Let's now go ahead and look at a bunch of examples so we can get lots of practice on this. So find the following indefinite integrals. What we'd like to do is try to find some part of the expression that we can replace with a variable u where the derivative also appears. So if I scan through this expression, I see I've got an x cubed plus 5. When I take its derivative, that's going to give me a square function. And I see the square is sitting out front. So if you haven't seen this before, it takes it'll take a few examples to get used to what we're actually doing. So don't be discouraged right now if you're a little bit confused. Through a few more examples, it should start to become clear. So I start by substituting for something. And I hope that the thing I substitute for has its derivative also in the expression. So is its derivative in the expression there? Well, sort of. There's that extra 3 that's sort of floating around. But constants don't matter. This just means I could rewrite it by bringing the 3 over to the other side. And now I see that there's an x squared dx, and I can replace those two things with a 1/3 du. So let's do that then. So I'm going to rewrite this integral as the x squared dx joined together. They get replaced with a 1/3 du. I can bring the 1/3 out front. What about the other part of the expression? That's an x cubed plus 5 to the 9. X cubed plus 5 I can replace with a u, so this becomes a u to the 9. And therefore, I've now reduced the integral down to something that's easier to deal with. How do I compute the antiderivative of this? Well, that would be a u to the 10th. And so antiderivative is u to the 10th, but I'd also have to multiply it by a 1/10 to cancel the 10 as it comes down when I take the derivative, because I need a 3 there. So this would be a 1/30. And that would get me the right coefficient when I take its derivative. And then I add a plus c. That's so the outside function I identified here as really the 9th power function. I found the antiderivative of the outside function. Now I can plug everything back in. So this becomes a 1/30 x cubed plus 5 to the 10th and a plus c. And there we go, we're done. Check. Let's check to make sure this is correct. And always do a check. The check not only validates your answer, but it also allows you to see what were the steps we did and what were they trying to undo in the chain rule. So here's the steps. We had this as our function. When I take its derivative, the 10 is going to come down. It hits that 1/30th to give me a 1/3. That gives me an x cubed plus 5 to the 9th. That's really the derivative of the outside function. That's the thing we are focusing on, and that's really where this 9th, u to the 9th came from. That's the outside function we were dealing with. But then I have to multiply by the derivative of the inside function. That was our 3x squared. The 1/3 cancels with the 3, and that was that x squared that was sitting out front. It was the derivative of the inside function. That's why there was an x squared out there. So that was the reason why we made this substitution, because we took care of the inside function and its derivative in one go to focus our attention on the outside function. So there we go, our check works out. What about this next example? So go ahead and try it for yourself. Take a few moments, pause the video, see if you can make a substitution and try to get it into a simpler form. Okay, so here we go. Let's see, what can we do? Well, I am bothered by the 3 minus 5t all on the bottom. The square root sign with that thing inside it, I'm kind of bothered by that. So I'm just going to try something, see if we can just substitute for that. Typically with these integration techniques, make a substitution, try it out, see what happens. If it doesn't work out, you can't spot how to proceed from there, go back, maybe make another substitution. It's trial and error here. A lot of good practice and good pattern recognition skills that'll get you there. So keep at it. Take its derivative, that's negative 5 dt. That means that negative 1/5 du is equal to dt. So I can replace the dt on top with a negative 1/5 du, and this becomes then 1 over root u. The dt gets replaced with the negative 1/5 du, which then becomes u to the negative 1/2 du. So there is the integral that we boiled it down to. And that's easy to deal with because that's just a power. And so we can find the antiderivative. That would be a u to the 1/2. I have to stick a 2 in front to cancel it. So now just to do a quick mental check, the derivative of 2u to the 1/2, the 1/2 comes down, cancels with the 2, gives me a u to the negative 1/2. Good, I've got it at that point. So this becomes a negative, oh, there's a plus c here. So it becomes a negative 2 to the 2/5 u to the 1/2 plus c. And so there is our antiderivative of the outside function. And so plugging everything back in, we get that a 1/2, power of 1/2 is the same as the square root. And so there is our antiderivative. Now you may have done something different. When you worked on this on your own, you may have come up with a different substitution, and that's perfectly all right. Let's maybe have a look. There is an alternate substitution you could have done here. What we're going to do is, instead of making the sort of conservative substitution where we just substitute for the 3 minus 5t, maybe we could get away with substituting for the whole denominator. So u equal to the square root of 3 minus 5t. Why would that work? Well, when we take its derivative, that becomes, there's the derivative of the inside function, which is going to appear on top, but the derivative of the square root becomes a 1 over 2 root 3 minus 5t dt. And that gives me then negative 2/5 du, moving the constants to the du side, 1 over square root of 3 minus 5t dt. And it's at this stage you go, ah, look at that. I made a substitution and I got the whole integrand along with the dt out of my substitution. So when I make this substitution, I'm going to carry on just down here a little bit. The original integral the whole thing is replaced with a negative 2/5 du. I didn't even have to bother with any of the other t's left around and replace them with the square root of 3 minus 5t. The whole integrand was able to be replaced with just the negative 2/5 du. And so that becomes a negative 2/5 u plus c, which, putting everything back in terms of t, becomes a negative 2/5. What is u? U is the square root of 3 minus 5t plus c, and so there is our result. And notice that they are the same. One substitution led to an answer, another substitution leads to the same answer. They'll lead to the same answers up to addition of a constant because the antiderivative is unique up to addition of a constant. So there are multiple ways to do this. Ideally, you're just looking for a piece of the integrand where the derivative also appears. So let's look at the next example. The antiderivative of sine 3t dt. So pause the video, go ahead, work on this on your own for a second. Okay, so let's have a look. Well, if the 3 wasn't there, I'd be happy, because the antiderivative of sine of t is negative cos of t. So there is a 3 there, though. I'm kind of bothered by that. So what I'm going to do is I'm going to substitute for that argument. And the derivative would then be 3 dt. So there's my substitution. Now, for the integral, I can replace the sine 3t with the sine of u. The dt I could replace with 1/3 du. And now I'm at that integral that I wanted. I substituted for the 3t, I now got that integral that I wanted, where the argument was just the variable itself. So the antiderivative of sine is negative cosine. And now I can plug everything back in. That would be cos of 3t plus c. And there we go. And don't forget to check. I mean, this one you could probably just mentally check in your head. Take the derivative. Derivative of cosine is negative sine. That's due to the outside function. The negative would cancel with that one. So we'd have a sine of 3t. When you multiply by the derivative of the inside, the 3 comes out, cancels with the 1/3, and you just get left with your sine 3t, which you wanted. So don't forget to do these checks when you've done your antiderivatives. So let's have a look at this next example. Take a moment, pause the video, and try it on your own. Okay, so let's have a look. We're going to make a substitution. What do we want to substitute for? We'll try to pick something out of the integrand whose derivative also appears. Often you sort of look for the more complicated things. Like there's this ln of u, it's trapped under a square. So maybe I could replace the ln of u. U is already being used as a variable, so I'm going to use w as my substitution variable now. Does the derivative of that also appear? Well, the derivative would be 1 over u. Does 1 over u also appear? Yes, it's there as well. So there's this 1 over, or maybe I should say du over u, which I can replace with dw. There's this ln of u, which I can replace with w. And so everything gets replaced. And the integral then becomes 1 over w squared dw. And now I can go to work on this antiderivative. What's the antiderivative of 1 over w squared? That's negative 1 over w plus c. Plugging everything back in, we get a negative 1 over ln of u plus c. Okay, how about this next example? So pause the video, have a look at it yourself. Okay, let's look at what can we substitute for. You managed to pick something out whose derivative was also in the integrand. Well, there's this reciprocal v function that's appearing inside the argument of sine, and the derivative of the reciprocal of v would be the reciprocal of v squared, which is also appearing. So maybe a good choice would be to substitute for the argument of sine, because the derivative is then negative pi by v squared dv. And if we just do a quick rewrite, that becomes a negative 1 over pi du is equal to 1 over v squared dv. And that is precisely this. So that can be replaced with this expression involving du. So here's our new expression, sine of u all over nothing now, because that whole thing on the denominator gets joined with the dv and replaced with negative 1 over pi du. What's the antiderivative of sine? That would be negative cosine plus c, putting everything back in terms of the original variable v. That's a negative 1 over pi negative, we can start getting rid of these negative signs, and that's a cos of pi by v plus c. And there's our result. So again, do a quick check. Work out the derivative of this thing, make sure you get back to the original. How about this last example? Okay, give it a shot on your own, take a few moments. Okay, let's figure out what we want to substitute for. So what do we want to substitute for? I want to substitute for something whose derivative is also in the expression. What can we do? Well, I could substitute for the 1 minus z. And let's see what happens if I do that. I'm going to do that one just because it takes everything on the bottom and just writes it as a single square root of a variable. So du is negative dz. So that means this expression then becomes z squared, well, z would be equal to 1 minus u. So where I see the z, I could replace it with a 1 minus u. Square root of u. dz becomes negative du. And at this stage, I pause and I say, have I made any progress? Well, I have. Because the numerator, if I expand it out, it's just a bunch of terms with powers of u. The bottom is a single power of u, so I could divide that into each of the terms above and just get a bunch of terms added together, all involving powers of u, and I could use the power rule for integration on each of those pieces. So at this point, I know I'm in good shape and I can finish the problem. It's now just a matter of going through the steps. So let's have a look at it. The integral of 1 minus 2u plus u squared. Square root of u, that's the same as u to the 1/2 du. So that's negative the integral of u to the negative 1/2. So I'm going to divide that into each piece. Minus 2u to the 1/2 plus u to the, well, 2 minus 1/2 is 3/2 du. Now I've got a bunch of powers. We can go ahead and work out the individual antiderivatives of these powers. So this would be a u to the 1/2, 2 minus a u to the 3/2, and that will be 4/3. I have to make sure that when I take its derivative, I get back the coefficient I want. And then this would be a u to the, add 1 to this, that would be a u to the 5/2, and 2/5, and a plus c. And so this becomes then negative 2, 1 minus z to the 1/2, plus, so I've got that negative sign out front, that's going to distribute across. 4/3, 1 minus z to the 3/2, minus 2/5, 1 minus z to the 5/2, plus c. And so there is our antiderivative. There's our antiderivative. And we got it by making that substitution. Now there is some flexibility in choice of that substitution. Maybe I'll just give a hint and you can work through the details on your own. There's an alternate substitution we can make. If I look back at the original, I can remember that, well, when I take an expression involving a square root and I differentiate it, the square root gets moved down to the bottom. Maybe I could have taken the whole denominator as my substitution. U equals the square root of 1 minus z. Then du would be 1 over 2 root 1 minus z. And then the derivative of the inside function would be negative dz. Or in other words, negative 2 du is equal to 1 over root 1 minus z dz. And notice that this whole thing is precisely that. And so if I do make this substitution, I can get rid of a lot of the integrand in terms of just du. The key, though, is that I need to get that z squared written in terms of u as well. So I go and look at my original expression and say, can I get z written in terms of u? Sure, I could take a u square, I could square both sides of this. That would be u squared equals 1 minus z, and then I could write z is equal to 1 minus u squared. And so there, I could use that to replace the z in the z squared. And I could get an expression on top involving u's, and the expression on the bottom, well, it goes away because it gets absorbed with the du. So this would boil down to, so the integral of z squared, that would be a 1 minus u squared, and the 1 over square root of 1 minus z dz, that gets replaced with a negative 2 du. And now I'm I know I'm done here in some sense that, I'm done in the sense that now it's just a routine calculation from this point forward. So I've made all the tough decisions, worked through all the details. Now it's smooth sailing because this is just a polynomial. I expand it out, integrate term by term. So I'll put dot, dot, dot here. You can fill in the details, but you get the exact same answer as we got above. So there is flexibility in the choices you can make for your substitutions. And so just be aware that even though you may be working on problems with someone else, you do it one way, they do it another way, you both could be right if you're both making appropriate substitutions. You plug it into Wolfram Alpha, it does one thing, maybe it does it differently than you do. That's fine. There's more than one way to do these problems usually. The one thing I just want to bring to your attention is that computers are ideal for computing integrals, and you have access to a mathematical software package at wolframalpha.com. So when you go there, you can just enter in the function you want to integrate using the command integrate, and it'll come back with an answer for you. So you can use this to check your homework and to help with your studying, but just be warned that you won't have access to Wolfram Alpha on quizzes and exams. So you're more than welcome to use this to check your homework and to help with studying, but you have to be able to do these calculations and computations by hand as part of this course. Okay, so just be warned, but you're certainly able to use this to help with your homework.